Hello. Yeah. Welcome, everyone. Thanks for coming to the Apex Meetup. Hope you didn't have too much trouble with the traffic or finding this place. So today's meetup is centered around Apache Geode and Apex and how they can be used together. So Ample has been leading this integration effort, and Ample has also sponsored this meetup today. So I want to thank them for the sponsorship. Also, this meetup is being streamed on a webinar, so we have folks joining remotely. We have 3 talks today, 3 speakers. Our first speaker is Nitin Lamba. He'll be talking about Apache Geode and Pivotal's leadership role in open sourcing it. The second one will be from Ashish Tirose, and he'll talk about integrating Apex and Geode and the in-memory computation, storage, and analysis. The third one will be from Suhas Gogate, and he'll be talking about an end-to-end ad tech ingestion pipeline application that ingests from Kafka and loads into Geode that was built on top of Apex and runs on Hadoop. So a couple of quick requests. If you have a question, please raise your hand, and one of us will bring the mic over. This is for the benefit of folks who are joined remotely. And second is after the talks, there's a feedback form, so please fill in the form, and you can basically enter information like the problems you're trying to solve, your use cases, anything else. And I promise your efforts will not go unappreciated. You'll get a t-shirt. So with that, I'll introduce Nitin. So Nitin is a co-founder of Ample and leads the product management. He has also led product development at Pivotal, and has held several key engineering and business roles in his career. And he's going to talk about Pivotal's effort on Apache.
Thanks, Pramod. Can everybody hear me okay? Okay, welcome. Good evening and probably good morning, or depending on who is watching the streaming. You must be wondering that just because we sponsored the session, am I authorized to talk about Pivotal and their strategy? I think the reason being the guys from Pivotal had some emergency last minute, they couldn't show up. But I figured that since I product managed Gemfire while I was at Pivotal, and I'm still a Pivotal alumni, from a pedigree perspective, so I can at least talk about what the thinking was behind some of this. What you saw in the video, by the way, was Richard Lamb. He was the founder. You missed the early part of the video, but he was the co-founder for Gemstone. And Gemstone has really long lineage. Even before it was written in Java, it was actually written in Smalltalk. Very few people know. So the company actually has longer than 15 years history. So what they covered was literally the more recent, right? Call it post 2000 kind of history. So the ideas are kind of, comes from more mission critical. One of the other co-founders, like Jags, who has been there with the company as an architect for the longest time, he comes from telecom background himself in the 80s and 90s. So similar, I would say, origins, right? As in mission critical comes first, and that's why you'd see. So today I'm going to talk about a few things. I'll change this sequence a bit. I'll talk a little bit about Pivotal's open source strategy, and then kind of get into the Apache Geode. How many of you actually know about Geode before you registered for the meetup? Very few. So it's good. I mean, I'm a product guy by design, so I can't talk too deep development. Otherwise, I'll get shot anyway. So it'll give you a good overview. Some of this content might be, very similar or familiar with what was presented last week. We had actually our first Geode summit last week, which was kind of an open forum for a lot of talks. So let's get rolling. So Pivotal, if you know, actually has a lot of open already. I mean, if you are familiar with RabbitMQ, Redis, Cloud Foundry, some of those are more visible open source initiatives that Pivotal has been running. I would say for several years. Spring is a big one. So anybody who is doing any Java development has at least come across Spring in some form. I mean, it's a love-hate relationship, I know, right? Scala guys don't get along with Spring and vice versa. So let's not get into that today. But at any rate, I mean, there is a lot of momentum behind Pivotal and open source in general. So what happened was that they were thinking, and they had a big data portfolio, right? And they were just scratching their head, because if you look at the new data revolution, a lot of changes have happened, And being open source is almost the starting point of a conversation. Otherwise, enterprises just dismiss you. They're kind of sick and tired of proprietary single vendor kind of setups. So in that sense, it was very obvious for Pivotal, okay, what's the next step? So what they did was in early part of 2015, they actually, in February timeframe, they made a huge announcement that's saying all of our data's products are going open source. It's a matter of when, it's not an if anymore. And as part of that, across pretty much all the data, big data suite, which is a sum total of GPDB, Gemfire, Hadoop was kind of open source already, but all of those were kind of made saying, okay, we are going to go ahead and commit it. Some are Apache, some are getting there, but in general, you can basically look at the source code and download it, whatever you want to do with it. So those are the four timing-wise that communities that were formed, right? Geode was the first one in May. The source code was released late April timeframe, and then came Hawk and Madlib in quick succession around Strata, and then immediately followed by Greenplum database, right? And Greenplum database, for people who don't know, was one of those three MPP databases. Like you have Vertica, Astrid Data, and Greenplum, right? And then Vertica was acquired by HP, and then Astrid Data by Teradata. So I think so. The question is like, what's up with Geode, right? So Pivotal is to Gemfire as Apache is to Geode, right? That's the best way of understanding it. And I think if you have ever seen any of these ads, right? So Gemfire was a gem, or for short, and then you sort of break open and get your gem. Geodes were sold. That's kind of the whole idea. Again, it could be a backronym or somebody trying to rationalize their decision for Geode. I don't know, but it is what it is. So whenever you look at Geode, it is the open source Apache version of what was Gemfire that was referred in the videos. So that's an easy one. Moving on. So in a nutshell, it's a distributed memory-based data management system, and it's kind of designed for essentially data-oriented apps. So what you'll see is it started out to being an application cache. I mean, you saw high trading, high volume sort of requirements. And then it sort of grew out of it organically, right? It was made production grade. One things were fixed at a time: performance, scalability. Also, it is transactional in nature. So it's in some ways it has tunable consistency. So you could use it as a purely transaction in memory store as well. So if you were to sort of say, okay, is this distributed Redis? Yes. Is it memcached? Also yes. Is it something else like operational database? Can you run queries? Well, you can run queries, but not SQL. You can run object queries on it. So it's kind of a bunch of different things, right? It's like six blind men figuring out an elephant, right? But it really depends on how you utilize it. It's kind of a development kit that way. And obviously a very powerful distributed data processing as well as event-driven. And we'll sort of cover some of that later on. I mean, what you would expect in Apache projects typically is that, hey, it's somebody did something and it's been run by one company, and okay, you know what? It's contributed, it'll probably get to production grade in 3 years, and then it'll probably get to maturity in 5 years. This is kind of a slightly different approach, right? It's already run in production or several use cases. These are some real 1,000 customers, right? I would say that it's incubating, but it's rock solid. And some of these use cases, just to give you a sense of timeline, right? Some of the early drivers were just around like, I just have a lot of data, or I just want to reduce my maintenance costs because my custom inbuilt systems are not scaling enough. And some of the elasticity needs, I want to be able to run it across 100 or whatever nodes like Red Richard was talking about. So financial services and US DOD were the earliest ones to sort of bite on it. And later on, when you started running into what I would call some of the real-time needs, low latency requirements started to show up. And then also people wanted some flexibility around where the data lives. Would it live in memory or would it be persisted or some combination thereof? And that's where some of the travel portals, some of the largest ones that were actually moved and been using this technology, on their websites and even online gambling was one example. Then you got into something interesting, right? When you have multiple data centers and then you need consistency for, let's say some very critical data across data centers and geographies. Think of those as, take a large travel site. Let's say they have 3 data centers or even banks. They have London office and Tokyo office. They don't want some inconsistency inconsistencies across the data centers, right, for some critical data. And those kinds of use cases sort of pushed us to further and further into, even wide area network related consistencies, right, replication and all the other things. And obviously, uptime was also a key requirement. So you can sort of start running it and almost forget about it. So 2016, like I mentioned, was kind of a turning point for this whole entire code base. It was contributed to open source. We've actually had our first milestone release in January. And then first Geode Summit was last week, Wednesday, right? You can probably find a lot of recordings and slides from that summit on SlideShare. Just look up for it. You'll be able to read up some interesting talks from real customers and what they have been using, banks and a few others. And also, it's kind of for speed and scale, right? It's not just one or the other. It's actually both. So just to give you a sense that, you look at the symbol here is actually China Railways, 3 terabytes of data in memory, right? That's a lot of data in memory, across a fairly large cluster. And about 40,000 transactions per second. People throw in big million numbers. So if you actually do the math for a per day, it's actually already in a decent millions, right? So like 4.5 or 6 million, whatever you want to do. Similarly, GE, I think this is a blog post you can actually search for on the web, the GE Water. And they actually deployed Gemfire in again, 17 billion records in memory, right? So it can really handle really large data sets. And this is one from India Railways, about 120,000 concurrent users. Now, mind you, these are not, this might look small for a mobile app or something, but these are the number of users that are making transactions simultaneously, right? That's kind of this, think of that as a peak load, right? Some other names, these are the publicly announced ones. They're probably a long customer list where Pivotal hasn't declared, so I can't talk about it. Impacting a lot of people, right? So just a nice tidbit, if you just combine China and India population-wise, that's like impacting 36% of the world population, right? So kind of, if you're making your trips during the Chinese New Year or in holiday season in India, I mean, you're sort of, the fact that the tickets are available or the pricing shows consistent, Gemfire is probably a role to play in there, right? Just to give you a sense of it. So this is probably kind of a higher level technical slide, but at least to give you a sense, it's almost at a cluster level, it's like almost a third generation architecture, right? It's peer-to-peer. So in some of the earlier, I would say generations, you talk about a master node and a worker node, right? Or make the master highly available. You'd see that in HDFS as well. But this is truly a peer-to-peer network. So the locator, which is kind of our internal word for a directory service, is actually optional. So the locator goes down, the servers still know what the other server is doing. And they are able to resolve, sort of network partitions, availability, and who is primary, who is secondary, all by themselves. So it's truly peer-to-peer. And then you can add servers. If you have a peak load coming up, you spawn 2 servers in, and they will know and discover each other and sort of scale it nicely. So it's a very nice properties that way. Like I said, it was a powerful development kit. So lots of interfaces, obviously Java and a REST interface. So if you want to have Python or even a direct, other language bindings. There are some other interfaces for adjacencies like Redis and Lucene and also Spark. Some of these are experimental, but sort of get the idea. So the top layer, this can act as a persistent store for a lot of these frameworks, computing or otherwise. It's a durable key value cache store, right? That's kind of another way of describing it. So what you have is that, again, trying to show you some different properties. So locator would know, this is not the data, but sort of have an information of what data resides where. And also sort of what's the state of the server. So it sort of keeps a kind of a manager role of health of the system. But then you can actually have different regions. We call them regions call it different key value maps. I'll cover that in detail in the next subsequent slides. And then you can actually, define whether they are replicated or partitioned or whether they persist or not. Several different options and buttons you can tune it for. And then towards the end, what you do is you actually persist it. Again, there are a few options, HDFS being one and some of the other, like the classic local file storage, as well as an RDBMS kind of connectors, right? So think of this as a fairly flexible in-memory layer that can, depends on what you want to do with data, but if it's on, and it's actually continue to run, right? It's fairly scalable that way. So one might ask, what makes it so go really fast? So it's like it tries to minimize copying, right? It doesn't do it unless absolutely necessary, and it's almost like transferring, in some ways, just the ownership of primary versus secondary without sending a lot of data across the wire. Minimizing contention points, reading versus writing, and some of that transactionality is also optimized. You can run user code in process where some of the functions can be pushed down, and you can sort of operate where the data resides rather than pull the data up to a client and process on it. And a bunch of other things, right? I'm not going to go too deep, but partitioning, parallelism, also the benchmarks. I was talking before the talk to another person of interest. I mean, we have tests that do unit level, distributed unit on the same machine and across machines. And some of these tests, at least at Pivotal, used to run across days. I mean, it's just like that. I would say that eye for quality has been there since the beginning, and we want to make sure any changes you make to the code doesn't break the existing, right, whatever suite. So it's been, like I said, it's been there for a long time, and trying to enforce that discipline, right, as we are even moving it to the open source community. So a few basic concepts here. Let me pause here. Any questions so far? Or so far so good? Pretty high level, hopefully. Talk about basic concepts. So you saw some of those, but let's dig deep on about what a cache and region and a member and some of these are. So think of cache as nothing but a way, it's kind of a unit in which you would store all the data on a particular, kind of unit of data management, right? And you can configure that through different options. You can have it statically configured through like an XML definition or any kind of descriptive language, or you can programmatically change that through Spring or Java APIs, or even from a command line. You can sort of make those changes. And this is nothing but a collection of region. Now, what you'll say, okay, now what is a region? So region is actually, think of that as a map on steroids. So think of the key value store we are talking about. That's like a key value store on steroids. Highly concurrent, distributed. You can have a virtual region that spans nodes, spans JVMs, and it'll actually ensure that it's consistent and data duplicacy and all that good stuff will stay in place. It's also observable. And what it means is that any changes you're making, so before you're making the change, during the change, after you make the change, all those points you have callbacks. So you can make any changes, you can do replications and say, okay, and the tunable consistency will be important, because I could say, okay, if my this data set is mission critical, I want write-through transactions. So I won't say commit until it's done. Whereas some of them is like, hey, my data volume is too much, I'll do a write behind, so it's eventual consistent. So some of those are just different ways that you can configure this, and it's all up to you, right? So it's tunable. So we kind of avoid the CAP theorem, kind of what should I say, the challenge or a problem, right? We say, okay, make this C actually tunable, right? And worry about the other two. Region types, there are different ones. You can have it local, you can have it replicated, like I said, across, like every member will actually have a copy of that data. So think of an application where you're making a train reservation. I'm sort of just using that for now since we have talked about it. Your seat availability and your pricing needs to be replicated data. But your users, if your users logging in from China mainland or from, I would say Asia or from Europe or from US, the users may or may not be replicated. You can partition them nicely and the system will scale well. Just an example, right? There is some data you would want consistency on, some data in which case you'll make sure it's replicated and it's always consistent. And others you can sort of, I would say, partition it nicely. Redundancy, again, a lot of options, overflow. This is, by the way, the whole list of different options. So anytime you configure a region from the command line, you'll actually see, okay, tell me what type of the region it is. And I mean, this is all documented. You can sort of go and have a look at. So again, different uses of your data. So it gives that flexibility of how do you want the system to treat your data, right? And you can have different regions with different properties as such. So something about durability, right? So I think we talked about write-ahead log. It's also about consistent recovery. I'll actually show that, and compaction. But then the idea is that you can actually store data not just in memory. You can push it to disk, and then you have eviction policies, spillover policies. All that is all tunable. You don't have to rewrite custom code and for every type of data requirement. Member is again think of that as a role. So a client is a member too. A server is a member. Any place where you can potentially store data is nothing but and it's kind of connected to the system, and then it's also embeddable within application. Like I said, it's a role, right? So if you're writing a Spring application, you can actually have a member defined, as a client cache too, right? And then you can sort of interact with it and then pull data from the server as required. There is actually a good section, and if you ever get to docs out of interest, where they talk about what different forms of, I would say, configurations of topologies that you can configure it to. And you can have it all the way from just a memcached kind of next to, like a Spring Hibernate or some other Tomcat server. Then you can have it in a client server fashion. You can have it client server within data centers or across data centers. So there are different ways of configuring this thing. Client cache. So this one is actually, think of this as if you need some data and then you need very frequent lookups of that data, you can actually create a local copy of that data within your client application. And that will be kept in sync with the server side. That's kind of a very simple example for it. But you can also run queries on that data, and as well as the notification is also bidirectional, right? Remember I told you about all the notifications before, during, and after a commit? You can actually listen to those events, and as soon as the data changes from a server, let's say from a different process, the client would be notified saying, okay, my cache is consistent now. So again, a lot of flexibility in how you deploy it. So let's talk about persistent, right? And this is probably the easiest illustration to understand. Let's say you have 3 servers in the grid, and think of these like you have, treat of these as regions, or these are actually referring to buckets. So buckets is nothing but like a smaller, several buckets will form a region, and you can deploy buckets elsewhere. That's kind of a smaller unit internally, right? But then you can treat this for regions as well. Let's say you have this configuration and one of the server goes down, right? So what will happen is the data is already there, but it'll be responsibility-wise, you'll say, okay, you know what, server 1 is down. For anything primary now, contact server 3, because server 1, I'm not able to communicate with it anymore. The health is down, right? So then you'll say, okay, what happens? What happens if everything goes down? Well, okay, that's always an eventuality. But by the way, this is the only one that has survived, well, not only, but one of the very few data services that has survived the famous or infamous Chaos Monkey from Netflix, right? So it has been tested that way. I think some of that would be eventually contributed in Geode. I'm not sure about the timeline, but I think there have been talks last week about it. But now, interestingly, let's say somebody might say, okay, what about if the first server comes up? So the first server, since it went down, is intelligent enough that you will fetch the missed operations on restart. So it'll wait until the new servers with more recent data will come online. And then it's called what's called propagation of delta data. So I restored my state based on the last write-ahead log I wrote and kind of whatever journal entry, and then I restarted it. And then say, okay, what has happened? 2 hours have passed, and I'm sure I'm not the most recent data. So I'll wait in line, let the other server tell me what my lost state is and lost transactions, and then sort of send it back and restart it. I think I'm doing okay with time, right? For 20 minutes? Okay. This is about operation logs. This again, there is some intelligence around compaction. So what you see between the two, right? Let's say you're changing the value, it's a put operation of a key value pair. And then you create it and you're kind of building these logs. When it comes time to roll over logs, what you'll do is you'll only pick up the most recent transactions. So if I change the key or the value for the very first one, you will not go to, include the old stale values, right? So that actually helps even making smaller logs, right? So this is a log compaction thing, right? That it actually works help. So functions, that's kind of my last concept here before we sort of open up more formally for questions. I think of those as like push down smaller stored procedures from a database parlance. You can sort of send those back to where the data lives. and it's kind of used for distributed concurrent processing. So this is like more like the MapReduce before it was formalized as MapReduce, right? It's kind of it's highly available. It's somewhat data oriented, and it's member oriented too. So you have options, right? I'll give you an example here. So let's say I actually do a small filter that I want on this particular region. I want to apply a filter which matches a particular key, right? It could be a regex or anything. So what it'll do is it'll actually go and send this execution saying that, okay, whoever has this region, tell me, what the values are. So it'll actually distribute. It won't even hit the server. So you can see on the top right there the data store partition actually doesn't match the key. It won't even process that request, right? So it's kind of intelligent, somewhat data aware, right? Where the functions need to be executed. So that's about it. I think you saw. You can go test drive the product, or not product. It's kind of a dev kit, like I said. It's kind of a decently growing community there. You can download the bits, play with the release directly, or actually it's a very simple process. It's pure Java, so between a Git clone and a Gradle build, you should be up and running. And literally, there's actually a section on Wiki which is like Geode in 5 minutes. I timed it myself. It took me 3.5. So if a product guy can do it in 3.5, I'm sure you can do it much better time, right? And thank you. Questions?
So Nitin, hello.
Yeah.
There's a question from the webinar. How should I reference the cluster? Is there a recommendation on how I should balance my queries to the data cluster?
Good question. I think you have an option. Typically, what we do is, depending, like I said, on the topologies, you will either have a client cache or a sort of a client that would be your entry point into the distributed system, and you would typically program a client to be that's where your application code will reside, and then the client actually it typically sends requests, depending on the configuration again, either to a locator or directly to the server, and then when failure happens, they themselves talk to each other and point you to the right direction anyway. And you have an option of caching that information. So the next time if server 1 was on, you'll actually now go to server 2 directly. So from a interaction perspective, you'll typically have in a classic application, you'll have a Geode client which will be talking to the distributed system. Oh, there's a question in the back.
Hi. Yeah, very nice talk. Thank you. So the value, what is its type, and what is the key also?
So think of that as Java objects, essentially. So whatever Java objects would support, it's essentially an object store, right? So key would be your normal. In fact, I've seen even keys to be more sophisticated, but it's essentially an object, right? You can have string, integer, or whatever, right? But you can have even complex objects on the value side. It'll just you'll probably make the region go larger, and that's kind of the only consideration. But you can have any tiny data. So
like the HBase polymer support.
Yes, so Geo doesn't, but I think you have to wait for the later on talks to actually answer that question. It's a good one. Right? Any questions?
Any questions?
Oh, I think there's one in the back right here.
You mentioned about one of the features you mentioned was it copies at the very last moment, doesn't copy immediately. Can you elaborate a bit more about it?
So now you're getting close to where the ice starts to get thin for me, right? But I'll try and answer that. I think what it does is that think of it such way, unless your redundancy of the system, right, how you configure it, right, for your particular region, and unless you have a strong replication requirement, like if you configure it through like a WAN replication, you will try and avoid data movement. So in that case that I showed you, so let's say if I already have a data copy and I am a secondary, for instance. So for me to be a primary, I don't have to worry about data or sort of making consistent I would say a lot of data movement. So in some ways, it's like trying to minimize, because network traffic, you sort of try and optimize for too much. But if you have configured it for replication, you don't have a choice. It'll actually make copies, whatever copies you have actually asked it to be. Yeah, it kind of depends on the configuration. Yeah.
You talked about it's transactional. Does it support two-phase commit and all that? You talked about it's a transactional system. Does it support
Yeah.
two-phase commit?
Yes, it does.
And all that?
Right. There's actually a very interesting locking service too. I mean, again, to sort of avoid a lot of those conflicts. But then, yeah, and all those for transactions, like I said, it's tunable. Whatever you want to do, chances are that it's already done, or you'll have examples to do it. All right, I'm getting close to my end time, so thanks again. And with that, here's an update for it. So, he has. Yeah. So I'll get it from the drive. You can use the
One, two. You can just talk.
Oh.
Just talk about.
What happened here?
Okay. One, two.
Yeah.
Hearing them all right?
I can hear him.
Might be able to give you a little.
Can you hold this for me?
Yeah.
Give you the other mic.
Let me have you.
That's a laser. Good point. Some technical problems.
Give me 1, 2 then.
1, 2.
Again.
1, 2.
There we are. And just turn that off.
I'm going to tell them to take
That's good. That's good. That's good. That's good. Babe. Okay, that's good. Hello. So our next speaker is Ashish. Ashish is a technical lead at Apple. He's seasoned in building large, scalable streaming, analytical, and ingestion solutions. And he led the development of one such application at PubMatic on top of Apex. He's also an Apex committer, and he's going to speak about Apex and Geode in-memory computation. With that, I'll hand it over.
Okay. Hello. Am I okay? Okay. So this talk is pretty much about Apache Apex and Apache Geode integrations, what we do. So having a good overview of what Geode is and what are the capabilities of Geode, we're going to see how those capabilities of and memory grade can work with the streaming technology and unfold a lot of new kind of feature sets which was not explored before. Okay, so first look at what is in-memory data grade. So in-memory data grades are a cluster of commodity servers which host the data in memory distributed across the servers, gives an efficient object-oriented model, object-oriented APIs to access the data, store the data, and update the live data. This features enables streaming computation framework like Apex to use this data grades to store large data, in streaming hot data into in-memory data grades like Geode. Which can be accessed in a fault-tolerant manner, in a very efficient latency. So this distributed in-memory data grids, which gives access to update the data in fairly less than a second. So this combined with the streaming technology gives a lot of application patterns which can work together, and this is what we try to do, having Apache Apex and Apache Geode use Geode some of the advanced features, and how it can integrate with the streaming technology like Apex. So that is what we're gonna see here in the next slide. So having a basic background of what Geode look likes and its capabilities, I'm just going to throw a light on some of the unique features of Geode, which is kind of very versatile and efficient. So one of the feature which Nitin did give overview on is the Geode's event notification framework. So Geode, despite being an large in-memory data grid, it also have a functionality to give a very event notification. Now, what that means for an application is, suppose your data is large and every time you want to get updates from the data, instead of making and get or put call, which itself has its application latency, application can use event notification framework. So there are cache writers and cache listeners. So what cache listeners does work is in a kind of after event notification callback. So your application gets notified once there are events or tuples added to the memory grid or updated to the memory grid. Uh, same as the cache writers, which kind of worked as a before event. So when the data or tuples to be go into memory grid, so can be used for a kind of a data validation and cleansing. Then there are concept of async event listener, which is kind of pretty cool. So once data get inserted or updated into a memory grid, this async event listeners give capabilities to do asynchronous action post the data is changed or updated into the system. So this features and already having an functionality of fault tolerant and a distributed memory grid can work in tandem with the streaming technology to work on certain features like designing a highly available distributed cache for a streaming application. Uh, all of this event notification framework, if the data is large, can be run on parallel or a serial. So serial, if you this serial event notification will give a fairly less throughput, but will ensure that the data is notified to a client in the same order the way it is getting changed. But there are ways to get this notification in a parallel, so which gives a very high throughput data access to the client. And it can also be all of this data can conflated at the server level and get notified to the client. Another interesting feature from Geode is called continuous querying. So suppose you have a fairly large data set sitting across your data grid, and you are interested in a specific key set, which is maybe a very small portion of the overall data, which you don't want to make frequent scan queries across your data grid, but you just want to get notified only when that particular key sets or even queries. So the cool part is if your objects are stored in the memory grid, and you know that there are it's like the same way the query is highlighted here. You want to get notified when this query pattern matches any data entries which matches this query pattern, you get notified. So there's a feature called continuous query. What it does, you register a query, and all your gigabytes or terabytes of data, when this queries, any data updates or changes matches to this query, are sent push to the client application, so that they just get those updates. So this is kind of a very cool feature which can integrate it with the processing framework like streaming technology. Also, like I mentioned, application can register for specific keys as well, so they get notified. So this is kind of a paradigm where you don't want to scan a large data set. You kind of freeze on a specific data which you are required on, send that data, register onto the server, and send that kind of register on the server, and you just get notified on that. So those were another cool feature. Now, how we managed to make use of these features and add certain functionality or improvements on Apache Apex. So I'm just going to talk about what integrations we did on Apex. So question, apart from data torrent folks, out of the audience, how many guys are aware of Apex as a streaming technology? Okay, so there are a few. So I'm going to assume that people are aware of the Apex streaming technology because that is kind of needed to understand this integration. So Apex in general is which provides a very scalable, highly efficient streaming technology where you can create a DAC to do a real-time in-memory computation and processing. So Apex, this is what a typical Apex application in terms of DAG looks like, where you have an input stream, input operator which reads the data from the source, which could be a distributed file system, which could be a message queue like Kafka or some other place. It will have operators which is gonna filter and compute certain aggregation and pass it on to a different operator, which can choose to write it to different store. Now, one of the key feature of any streaming technology, and even Apex in particular, is to ensure the resiliency of the entire platform and ensure that platform is able to recover from the node failures. How that is obtained is using a functionality called checkpointing. So platform underneath, without user intervention, keep doing checkpointing at a periodic intervals. So what that means is, so Apex has a concept of windowing. So at a configured Windows, Apex platform ensures that the state of the object of all operators get checkpointed at a state. So in case of any node failures, Apex platform will be able to restore that particular operator from the last previous checkpointed state, and to ensure that the DAC can recover from the node failures. Now, in the existing Apex application platform, this checkpointing, which is a very critical feature to ensure reliability, was done in HDFS. So what that means is periodically the object state gets stored into HDFS. Now, we all know that HDFS is a fault tolerant distributed file system, which is a very proven technology for a large scale file system data access. But what it is not good is writing small number of files or objects, because despite giving good fault tolerance, it has its own latency of writing the data in HDFS, because once that you issue a request to write the data, that data gets replicated across multiple nodes. So that feature kind of then becomes a bottleneck, because think about it, you have a DAG application which have hundreds of operators. Each operators, after every configurable seconds or milliseconds, writing its object state to HDFS. So if your HDFS writes are slow, or you have fairly large applications which are doing a lot of checkpointing, can in turn slow down the entire impact the performance and the latency of the application. So what we kind of propose now, since there are efficient and fault tolerant in-memory data grid like Geode, why not use Geode to checkpoint object state instead of HDFS to an in-memory technology? So previously, the upper part, which looks like an in-memory layer, and the lower below is the distributed file system. What we have done is we changed the Apex platform's checkpointing, instead of doing into a file system, into a same in-memory layer into a Geode. what it will mean is for a larger application which have large number of operators will give a much better latency because the writing data into Geode, which is an in-memory cluster, has a much better latency than writing data into a distributed file system. And all of the entire platform now remains into an in-memory layer than going into a frequent file system IOS. So kind of you get rid of one of the file disk accesses, which can potentially have impact on the overall application. So for this feature in the Apex open source community, we submitted a feature which can. So Apex already have a checkpointing storage agent, which kind of interfaces where user can write a different storage agent, which we write one for Geode, which does a checkpointing into a Geode cluster. We submitted the patch, and which is kind of merged into a or on the way in flight to merge into upcoming Apex releases. Another scenario to talk about the usual now having this Apex Geode integration, which looks like this. One of the usual pattern what streaming application does is they read the data from some source, they do some filtration computation, and usually the pattern is to write the data in some NoSQL database, which is available for further analysis or which can power your analytics dashboard or others. Now, so what it means is usually streaming application end up writing data to another NoSQL databases. Now, this NoSQL databases, the kind of efficiency and the feature it's supposed restrict the features of the entire your application which you're trying to do. Now, let's assume you have a real-time application which is reading data, computing aggregates, and writing into HBase or distributed other distributed stores like MongoDB, which does not have features like transactions. So what we thought of, why not write a Geode operator? So Apex application should be able to write this data to an in-memory Geode cluster, which will give a much more higher write throughput just because it is purely in memory. So we then integrated a Geode output operator which can take different kind of data set. You can have a pure byte arrays or a complex POJO objects which get returned to a Geode cluster. Now, how an application benefits from this? So what are the benefits of writing this data into an in-memory Geode cluster? Just more than a performance gain. So one of the cool things is Geode already have a pre-built query support. So now you have an application which reads, computes, and write to a Geode in terms of POJO. It is querying that data is fairly easy because Geode comes with the tools where you can query the complex nested object with the object query language, which is similar to SQL. You can query the nested objects, do a SQL-like queries if you have indexes on top of that. So that is one thing. Sorry.
There's a question on the webcast.
Sure.
What response times are you able to achieve on queries?
On Geode queries?
Yes.
So it's not Geode queries from Apex, or it's just Geode queries?
So the person who asked the question, could you qualify a question that it's Geode queries or Apex to Geode queries? I believe it's Geode because this was part of the first.
Okay, so so it's so this kind of covers based on what Nitin has already talked about. So even despite being Geode span across multiple distributed nodes, for query mechanism, it's have a lot of efficiency. So first, your clients are already application aware. So you're querying for a particular data, it's already have a partition logic where I know where to find this specific data which qualifies for this query. There is a concept of a single hop. So even if your data set is large and sit across multiple node, it goes and find as the qualifying node which is there and try to satisfy that query in one single shot. Also, there are yes. Is it
So
full?
what is that node is in a different geographic?
Okay, the different geography.
Yes.
Okay, so usually people don't span one cluster across geographies. What they end up do is for stuff like disaster recovery, or what Nitin already mentioned. What you will end up having is you will have one geo cluster and a different geo cluster in a different geos with this feature called WAN replication. Now, WAN replication is a built-in feature which ensures that at application level you don't need to do anything. You just configure, this is my London region, this is my LA region. So the platform ensures that both regions across WAN with the WAN replication should be in sync. So
Yeah, so what is the response time for that, the latency? It is depends on the WAN capacity.
okay, so WAN replication, like I said, your normal queries never reference WAN. It is a feature for a disaster recovery. So that comes into a picture. If your entire region goes down, you have different, the query gets routed to a different region, which in a concept of the cluster failures, and that definitely, that latency is impacted by your, because your query is now going across WAN to a different region. Which okay, for the initial question which I was giving in justification is the single hop, even despite being a large scale in memory grid, with the single hop, the query qualification and finding the right node, it's able to fetch the queries in few milliseconds. So it's Geode, pure Geode does not have a scan like feature. They do have indexes where you can run complex queries. They have function push down where you can, if you have if you want to get a larger data, instead of getting all of data to a client, you can probably send your computation there on only the result set. But at a transactional level, all the data get to an application in a few milliseconds.
Another question. Apex is a native yarn application. How does Geode interact with yarn?
So basically, Geode doesn't interact with Yarn altogether. So same way, Apex is kind of on top of Yarn, which uses Yarn's processing framework for a deployment and managing of Apex application. Geode is kind of a standalone cluster, so that can get deployed on a Yarn cluster or any bareboard machine. So what Geode requires is you can configure, you can give it an ample amount of memory and spawn Geode cluster on any machine. And Geode already have some sophisticated deployment tools. So there are CLIs which can use to manage and deploy cluster. But in a shorter summary, it does not require YARN. And if the question is about how they interact, YARN, Apex running on YARN and all of these integrations, Apex will have an embedded Geode client. Let's say Apex as an output operator will have an embedded Geode client which will be interacting to a Geode cluster, which may be on the similar node, similar network, or the cross network. Okay. Okay, coming back. So it's kind of lost. So what I was explaining, so the benefits of writing this data in Geode store. So one is you're computing, you have your POJO complex nested object, you are writing into a Geode, and you can just fire up the queries to the OQL queries to see your analytical results as the data being streamed. So Geode is meant for a fairly large number of clients. So it's not it's grew up being a transactional system, so it has the ability to handle large concurrent queries. So you can have a system which is streaming and writing and updating a fairly large amount of data. The same way you can have clients which can do analytical queries using OQL. Another benefit of writing streaming data to Geode is the visualization support. So Geode, if you guys are aware of an incubating project called Zeppelin, which gives a simplified visualization graphs and have a concept of a lot of interpreters too. So they have Spark, Flink, I guess a lot of other SQL interpreters to simply visualize. So, and they can get embedded. So Geode is already part of that. So again, use case to think about, you have a streaming data which gets ingested into a Geode. You can just fire up a Zeppelin visualization tool to see that how your data is streaming and getting updated in real time. Next benefit, another benefit which Nitin already covered, it has a sophisticated persistent mechanism. So you can choose to have persistent data get persisted into a disk. You can choose to have your data get persisted into a distributed file system like HDFS. So, and despite that, data do get replicated across nodes. So the node failures, node, if there are node failures, the data from residing on the different nodes will serve the data queries. If the entire cluster goes down, the persisted, so that cluster or the region get recreated from the last persisted data. And Geode has a very good transactional support, which we will see in the one of the integrations how we made use of. All of these are configurable. So you can have a disk persistence, you can go to a finite level, how to how much of when do you want it to flush the data, do you want a persistent to be synchronous, asynchronous, many of those things. Okay. So this is so for this feature as Apex output operator to be able to write the data to Geode, we had submitted this feature to Apex community, which the pull request is accepted, and again it will be available in the upcoming Apex releases. Okay. Sure. Okay, now there are these two features which we talked about, writing data to Geode and checkpointing, which is already there in the Apex community. There are other future integration which we are proposing, and which to culminate it with integrated with Apex, which I'm just going to talk about. So like I said, Geode has a very good transitional support. So how a streaming application can make use of this transactional supports, because real-time streaming platforms and transactional system has never been used together. So there have always been two different parts, but how they integrating together can make use of to achieve exactly one semantics which is required in streaming application. So that is what there's one use case around that. Then how about all of the data, your if your lot of data is already residing in Geode cluster, how can you do a real-time analysis on data? So there is an integration proposal is to write an input operator which can read the streaming data from Geode. Then one of the efficient thing is to every streaming application tend to have a reference lookup cache. So how about using a distributed cache operator in Apex? And then if your application also has supports a batch or batch queries, or suppose have a need to compute some complex analysis which cannot be done at application level. So for that, having a scan operator which will send the computation to servers and get that result, which can be used in streaming applications. So let's go over some of those. So transactional operator. So streaming technology usually comes with semantic models. So there are usual data streaming technology or even ingestion pipelines tend to have the de facto three semantics of data flows. So there is at least one semantics where your data is ensured to get delivered at the destination with a fair amount of duplication in case of certain scenarios. Then there is at most one which nobody, I don't think, ever uses, because which can allude to a data loss. And then there is exactly one semantics which requires a lot of plumbing and integration with from input to processing to external system to achieve, because that's a difficult part to achieve in the large scale streaming technology, to achieve exactly one semantics. Uh, to achieve that, what it requires is a good amount of checkpointing, and where the data is written into that data store needs to have a transactional support, because you have a data which is being read from your input sources. They get aggregated, and the same window which gets snapshotted and goes to an external store, that external store needs to support transactional to achieve, and all of that wire together to achieve that exactly one semantics. Now, if your destination store does not have transactional support, it's very difficult or close to impossible to build an exactly one semantic pipeline in streaming. So that's why what we are proposing is to have a transactional operator which will write the data in Geode in a transaction fashion, because Geode already support transactions. So that's yes.
So you said you write the data into the external source and it has to have the transactional feature, right? So what if that external source is a community hardware, it doesn't have anything?
It doesn't.
It doesn't have that feature.
It's not in the hardware. It's your data store as an application needs to have it. So if you're writing to a RDBMS system which comes with a transaction support, but if you're writing to a NoSQL database, let's say HBase, which the vanilla version you do not get transactions, so that is good.
So you mean to say to the database?
Yes, database. Okay. So next feature integration with Apex streaming processing framework is an input operator. Now, use case is a lot of data which could be a raw data or a pre-computed data already resides in Geode, and a streaming application need to source this data. So all of my data which is already reside in Geode, I want to do a streaming analytics, or maybe I have already running DAG. I want to also make use of the data which resides in Geode cluster. Uh, so the proposed idea here is to have a Geode input operator which will utilize Geode's event notification framework to. So Geode has an event notification framework where client can subscribe that, hey, every time there is a new entry added, push it on to me. Every time there is an update. So have an input operator which will use event notification framework, which get notified every time there is a new entry or new tuples added into a Geode data store, and pass it on to a real-time streaming pipeline. So that's the use case and integration we have proposed for streaming Geode data in Apex. Uh, Next is the cache. So any distributed application tend to have references lookup. So it could be some ID to value mappings, and in a real scenario, no matter what plain simple application is, there are always some static data an application needs to have. Same is the case of streaming applications. What I've seen is how these caches are being maintained in the real-time streaming is all the computation nodes or operators, they integrate with the external system, maybe an RDBMS, maybe S3 or file system, where this all the static data which don't get updated so frequently, maybe once in 20 minutes or a half an hour. They go and query this data, maintain it into their local collection, and use it as a reference ID lookup cache. Now, one of the hardest problem in the computer science as well is to efficiently invalidate the cache, because how you're going to tune your application is go and query and check if that data is changed, my static data has changed, or there is any update. So there are some caveats to that. So now you're gonna either poll for that data source every configurable amount of time. Now, to to build a highly available and distributed cache operator, what we have again thought of is to use Geode's event notification framework. So you have a Geode distributed cache operator in Apex, which will give this update. So application does not have to go and call for any data from the external source. If the data gets changed, application will get notified, hey, this particular key has changed or this particular key has been removed. So invalidate your cache synchronously, so you don't have to, your polling cycles are reduced. So that's one of the feature integrations which we are proposing, where we building an Apex operator which will use this notification and key registry features to power a distributed cache operator. Sure.
So this Apache Geode, you mean to say it's really good for the structured data? Sorry. Structured data, right? I mean, what if it is a non-structured data?
Yeah, it is. So Geode at Geode is a key value pair. So all of these features, even if let's say your data is not structured and what you're storing is images and a blob, what all of this feature is works on your key. So your keys get notified. So even if you're storing a blob and what you register this interest, not, let's say you do not have a structure where you can formulate these queries, but you do get notifies on your queries where there is these data sets are updated or added. So it can, the good thing is it work at both level. If you have a structured data, it will work efficiently because you should be able to write queries like this. But let's say if you do not have a structured data, you'll still be able to use those queries based on your keys. Your keys changes, updated, you're still going to get those notifications.
But it has to be on a transactional database for the appropriate performance, right? For the external data source.
Need not be. So here in a particular.
So I can use any NoSQL database.
No, this particular feature continuous query is part of Geode. So your data is, so I assume your data is residing in Geode, and then you should be able to use this continuous queries to get this data, and then make certain integrations like managing a cache operator. Okay. And next integration. Okay.
So two things. One, you're talking about using Geo to speed up application. Did you benchmark any sort of real application with real data set to see how much of actual speed up do you get from that?
So we did, so a couple of integrations what we did. So one of the speed up boost which you'll see in an order of magnitudes, and which I think does not even require any proof points, is look at the checkpointing use case where your data gets checkpointed into a distributed file system. So it is straight away a big difference than writing into a distributed file system than writing into an in-memory layer.
So I understand the advantage, but did you actually benchmark? Here's the real application.
Yes.
With real data, with checkpointing. Here's how long it took. With Geode, here's how long it took.
Yes. Yes.
And what were the results?
So by just replacing the HDFS based checkpointing, having an application which have operators which are configured with exactly one semantics, which keep doing checkpointing. So we had it running on HDFS and we had it running on just Geode cluster with the in-memory checkpointing. We saw micro benchmark that the checkpointing period has a better latency, and the checkpointing is 2 to 2.5 times faster than the HDFS based checkpoint.
And how much does that account for the total application time? Did the application itself speed up by 100x, 2%?
No. So that so for a checkpointing it may not, because that depends on is your application is actually getting hurt because of checkpointing. So let's say you have a fairly small application and which does not incur a lot of checkpointing. So
did you check with any sort of real application with real data to see any particular application that actually used that, and what was the result?
Yes, so it's very straightforward. So you have a smaller application where object states are very smaller. So then your checkpointing into HDFS or end-to-end memory is not going to give you a performance boost. So here is one of the data point which I can give, because I was at Pubmatic. We were managing a large scale application. So there application DAG was fairly large. I guess, I don't know if it's right to quote, was one of the biggest enterprise deployments, but it was one of the initial large scale Apex deployments, which was taking an overall processing operator nodes used to spawn across 150 nodes, and cumulative memory size of the DAG was more than 2 TB. When we moved from so we had a migration project where we moved from AWS to on-prem. AWS HDFS cluster gives a faster latency because there all of your HDFS is made up of SSDs. When we move to on-prem, where your HDFS is made up of disk, we started getting a performance downgrade because of the checkpointing. Because what happened there, we had a fairly large application with large number of partitions, and that was a time when actually we have gone through those cycles. So we for the first time we had to go and sit down and see that how many of our operators actually require stateful and statefulness. That was all because the checkpointing was hurting the application. At times it becomes so severe that uh, let's say your HDFS writes are very slow and you have a large application with large partitions. It eventually really slows down your entire application. It to that extent that it starts building an lineage on your buffer servers, and it eventually used to lead to crashes as well. So that was a case study which we had seen, that at Pubmatic we had to go through all the process of. No. It it was when I was at Pubmatic. It was like more than 6 months back. So, yes, that's what I said. So so there is an machine data demo. There are applications which are fairly large, and which gets when you create large partition, it get bugged. So that is where we saw the performance gain to 2 to 2.5 times. Okay, thanks. Yes.
So when you say you have that AWS,
Yes.
when you say SSDs, so would you say that the checkpoint is the performance of the checkpoint is proportional to the RPM of the disconnect, or is
Yes. So see, it's when you're doing checkpointing in HDFS, so HDFS read and write latency is configured by how are you making your HDFS? You are making your HDFS is out of JBOD, out of SSDs. So obviously SSDs have much more faster than a JBOD. So obviously, so there your HDFS write latencies were faster. Okay. So what am I doing on the time? So this is anyway a last integration. So what it talks about, it's you have a streaming pipeline and you want to you have a small piece of analytics need to be done now, which you don't need to do frequently at a seconds level, and that analytics piece needs to run on all the data in the in-memory data grid. Now, one of the things which an application needs to do is to, oh, I have like 2 TB of data which resides in my in-memory data grid. I have to get all of that data to client and run those aggregation or whatever my user-defined function is. So Geode already had a function where, same like MapReduce, you can ship your computation to a data itself. So Geode node not only acts as a data store, they acts as a computation as well. So you have that small piece of UDF which goes to a Geode server, gets run there, and the results get combined and sent back to the application. Now using that feature with some sort of scan operator. So having a scan operator which you configure with that application logic, which periodically pushes that computation to a data grid and just gives the result set. Then so using that application pattern we are proposing to have a geode scan operator which will have a predefined computation go to a server and the result state gets streamed into an application. So that's what pretty much it, all the integrations. So some of them are already there, which will be out for you to use and evaluate in Apex and Geode, and some of them are in flight, which is being worked on.
Any questions? Anything on the web? Thomas? Anything on the web? Okay, so we'll start the next one in 5 to 10 minutes. So if you want to stretch your legs, have a beverage or pizza.
Yes. Should I?
You don't want to face right into the speaker. Should I keep this alongside?
Yes. Let's do one thing. Where is the talk? We go inside. Documents. Three. And
Let me see how it shows up here.
yeah. It's 300. Better, right?
Yes.
Okay. And then you logged in. So once this is done, we'll switch. Or you want to just keep? Maybe it's better to just. Let's just share your screen, right? Let's try right now. Because you have the same slides.
I don't. You mean like I can just bring up the slides which I sent you, right?
Yeah. No, actually, not. Let's do this and then we'll switch. Okay. You have the mic. Yeah. Yeah.
This slide switcher is this one. I'm gonna try doing away with this mic.
Okay.
Pretty sure that's where all the noise is coming from.
Okay. We'll get rid of this.
VHF. Yeah.
I have not used it. I just used the arrow keys.
Why don't we just take this
I think
off
that
for
was
now?
Nitin brought it.
And just
So,
try the other one.
so I'm not quite sure.
Yeah.
It's not. Maybe not well shielded.
So will you just bring yours next
I
time?
can bring my
and
PA.
then we're
I
gonna
can bring
keep-
my own PA next time.
Okay.
No speakers.
Okay.
You know, we can try that. It's definitely.
Actually, I'm
Yeah,
thinking.
I definitely don't want to do that.
Should I use this mic or?
No, they'll put another one. So this is your slides, or this is just your screen share. I'm wondering if instead of maybe switching in between, might be easier. Okay.
Here.
Okay. Our next speaker is Suhas. So Suhas is a Hadoop veteran, and he co-founded Apache Ambari, and I think almost all of you are familiar with Ambari. He's also held architect roles at Yahoo, Pivotal, and Hortonworks. He was a chief architect of Pivotal Hadoop distribution and was architect of Hadoop installation management and monitoring products at Hortonworks. So, and he's going to speak about an end-to-end ad tech pipeline from Kafka to Geode on Apex.
Thanks very much for the introduction. So today actually I'm going to be the demo guy. So I'm going to show a demo where the whole AdTech pipeline, streaming pipeline that we have simulated to do the streaming analytics on the various ad campaigns, advertisement count, metrics through data torrent Apex and storing that data inside Ampool. So now, as I'm going to show you some demo about the Ampool, I'm just going to talk a little bit about the Ampool, what the Ampool platform is, and so that would actually get you some more context that way. So you guys, I mean, heard about the Geode. So Apache Geode is basically the in-memory distributed in-memory grid. So we actually, oops, so it's not changing here. I change it over here. So just
Oh yeah. So let me give it.
so my screen is shared already, right? Okay. So Ampool is also an in-memory store powered by Apache Geode. So Apache Geode, you know, that has a lot of good functions, and primarily the data set abstraction that we have in Apache Geode is a key value store, right? So we have a distributed key value store for fast lookups or low latency transactional applications. But we are in Ampool, we are enhancing it to really support the analytics type of workload. So many times, I mean, people have a problem that they actually want to ingest the data very fast into memory, and the data should be really quickly available for analytics. So for, I mean, many streaming analytics or batch analytics workload that we have seen, that typically data comes in hourly batches, right? And it takes a lot of time to really load that data back into the analytics system. So if you can really analyze that data right when it gets ingested into the memory, right? I mean, that's where the real power of Ampool would help you in doing the fast data analytics. So what we actually add on top of Geode, we actually add basically a table store. So we actually have a data structure, it's a table abstraction that we support in the memory stores, where you can actually store the rows with multiple columns. Uh, this is again, as I mentioned, this is for high throughput analytics sort of applications in memory. Uh, we are actually also supporting the smart data tiering. That, I mean, today we have basically the SSDs, RAM. We are going to have non-volatile RAM. I mean, these are the hierarchy, and then we have a disk. So how do you actually uh, address this hierarchy of storage? We are having support for that. We also have a catalog where lots of, I mean, this our table abstraction, we call it as an M tables. So all these M table catalogs actually we also support inside the Ampool, where we keep the metadata about tables so that we can access them efficiently. Uh, uh, we have security, as well as we have a shell. That way you can actually go and access these table metadata. I mean, view them on the client CLI side. I mean, using the command line. I mean,
What do you mean by native interface there?
so native interfaces is essentially you want to
Sure. Okay. So Java API is our default API for connecting with other stores that have been written using Java, such as HDFS, HBase, Hive, ORC, etc., etc. However, all the new non-volatile memory technologies that are coming out, the first version of the interfaces that are going to come out are going to be in C, and these are the native interfaces. So, in addition to Geode, which does not have the native interfaces, we basically added native interfaces in the sense that we can actually, let's say, pvm.io or the new the new mnemonic project that is coming out of Intel. So we will be able to interact with those. So the time that all these non-volatile memory becomes sort of commonplace in commodity hardware, we should be able to utilize that.
Now in Ampool, actually, we have this in-memory store, but that is backed by multiple pluggable store managers. That means you can have HBase, you can have HDFS as your persistent data store underneath. So we are agnostic to, uh, what sort of underlying persistent storage that we want to use. Also, actually on the north side, the interface wise, you can actually run the Hive queries without changing anything. You can actually have the Spark or MapReduce jobs that can run without any changes. Your application logic can run, and that can actually use the data from the in-memory mtable store. So we have the north side interface where people can use their existing tools, as well as for persistence layer we can use the pluggable storage layer, whichever people currently using. So here are some high level uh, bullets about what the value we are bringing in addition to Geode through Ampool. So I'm going to show you a demo where, as I mentioned, that we actually are simulated the complete advertising technology pipeline, where we have essentially said we have typically in advertising technology, what you have lots of users. You have basically the content publishers, and you have the advertisers who actually have lots of ads or campaigns that they run on the publishing websites, right? So typically, the users, content, and ads, they have some sort of an interest, and typically what these publishers or the ad exchange does is to essentially match the user's interest with the specific ad interest. And whenever a user goes and sees a particular content, actually the specific matching ad is essentially shown. So we have tried to simulate all that stuff. So typically in this ad tech pipeline scenario, all these events like user goes to a website, downloads a content page, get to see the ad, is essentially comes as a set of events which typically are called ad server logs, right? And those are essentially analyzed to find out which ads are doing better, which campaigns are doing better, how much revenue they are making, and so on, because each ad view or ad click or ad conversion event actually has some dollar amount associated with it, right? Also, there are bunch of updates typically happen not as fast, but typically happens to users interest or users profile changes. The content profile, sometimes content actually in fact changes, or even ad keywords or ad interest also changes. So those events also we actually take into this pipeline and try to actually show you how the streaming analytics works. Oops, uh, So as I mentioned, we have this ad server logs, as well as we have an updates to users, contents, as well as the advertisements themselves. All they basically come inside a Kafka. So we have a Kafka cluster. From the Kafka, actually Apex picks up all those events, and Apex basically stores those events into Ampool M table. But at the same time, Apex also basically does the streaming analytics on it by computing the top 10 advertisements based on the advertisement views by the users, or top 10 campaigns based on the clicks, the top 10 clicking campaigns stuff. And then essentially the data gets stored into it. This is a very high level view. We also are basically showing the visualization through data torrent. Now, Apex to Ampool, in which the next slide would give us the better. And then we essentially visualize the data or ad metrics or campaign metrics through data torrent dashboard uh, for the various involved parties.
What's the use case, particular use case for this? Use case. I mean,
Use case is, this is advertising application or advertising platform, as I mentioned, where you have your website and you are basically publishing the contents, you are accepting the advertisements from the advertisers, and then on the background you need a lot of analytics or sometimes the streaming analytics to understand how your ads are doing. I mean, advertisers are giving you the ads, but they also want to see, I mean, how much I'm spending in real time, how many users are really coming and seeing my ads, how many of those are viewing my ads versus clicking on them. So all that analytics in real time is what we are actually showing you in this specific use case.
Makes sense.
And for that, we are actually using the Ampool as an in-memory store for actually streaming the data and storing in our table abstraction. At the same time, while actually doing the streaming analytics, while processing these ad events, we are also doing the lookups, very quick lookups to our in-memory store to augment certain data that is coming through ad server log events. So these are the typical things that streaming analytics require to annotate the data, right? So this is where you have ad server logs, you have a content ads or users updates. They are coming into essentially Kafka, and then in Apex context. So So this box is where you have these Apex operators. Now the ad server log is actually basically processed through Apex set of operators, and we are going to see the complete DAG soon. And then it basically computes the top 10 campaigns which are viewed and top 10 ads which are viewed or clicked. And then essentially that stuff is stored back into the in-memory store. So you can see that in streaming, actually all that latency is very, applications are very sensitive to latency. So all that storage happening to the M table is, and this thing is very latency sensitive. So, and then it basically gets back and visualized through data torrent dashboard. Essentially, these operators in Apex directly are storing the data into M tables for essentially the what we do is we store these users, ads, and content inside the Ampool, and we run the batch analytics on top of it. As the data is coming through streaming and getting stored in Ampool tables, we also run the batch processing so that we can find uh, the best ad that matches the specific user's interest, right? Because users' interests are changing, content is changing, ads keywords are changing. So we are doing the batch analytics to really find out for any given user what is the best matching ad to serve. And then we essentially generate this basically content to add and user to add mapping table. And this information is essentially used in our simulator or data generator to really pick up an ad for when particular user is randomly chosen for showing an ad. So you can see the whole closed loop over here, and all that requires an in-memory store accesses that helps you actually drive the pipeline a lot faster. So this is where I would end the slides, and I'll just show you now the demo. So I have the Hadoop cluster, HDFS, Yarn, and Kafka installed through Ambari. I have a single node cluster on Amazon, where we have these things installed through Ambari. I have installed. Actually, we also have a support installation of Ampool through Ambari. In this case, I haven't done that, but we support that. On that single node also I have installed the data torrent as well as the Ampool. So I have this data torrent application at stream. So I'm just launching this application. So what is the data torrent or Apex application? Is basically it's a DAG of operators which pick up the data from Kafka topics and processes and output that into M tables. Whenever during the streaming processing it requires any accesses to the data which is already stored in any memory store, it basically makes the fast lookups. So my application is essentially launched on the data torrent platform, single node data torrent platform, and this is hosted on this Amazon machine. So we can go and quickly check. Oops, I think this is failed. So we have some glitch here that we need to actually start it at least 2 times, I mean 3 times. So this is a real demo. uh, okay, so now you can see that first attempt failed, the second attempt is accepted, it is failed, and by magic now I'll show you that the third attempt must, yeah. So you can see here. So what it is doing is essentially it has a bunch of operators. So data torrent actually uses its streaming application uses the yarn to basically launch the bunch of containers, and each container actually runs a particular operator. And then operator basically some of them are the source operators, some of them are processing, and some of them are sort of sync operators. So source operators essentially read the data from Kafka, the processing operators process them in a streaming fashion, and the storage operators store them into Ampool. So if you see, there are basically 18 containers have been launched. Right now there is no data flowing. And if you see, this is the DAG of operators. So we have this 1, 2, 3, 4, and 5 operators which are reading the data from Kafka topics. Now, out of this, four top two and the bottom two actually are sending them to the storage output operators, which are mout adds, content, server log, and this thing. Which these operators, storage operators, are nothing but just streaming the data into Ampool, because we actually run the Hive query on that streaming data. I mean, streaming in the sense in a batches or hourly batches, we actually run the batch analytics. So we just stream and store that data into Ampool. Now we also read the add server log. This is another operator which passes the add server log events to add server stream counter. So that stream counter nothing but basically just finds out how many for a given ad or for a given campaign and a given type of event, how many actually events happen. So it just counts them. So events are either clicked events or view events or conversion events. That means whenever ad was shown, it was just viewed. Ad was shown, it was actually clicked. So those events we just want to count per ad and campaign. So that's where, and then basically it sends out those things separately to to add a top 10 counter and campaign top 10 counters, which computes the top 10 counters in a given specific window. So we have about 20 seconds worth of window. And then essentially those metric, I mean, those top 10s are also basically stored back into Ampool for visualization. I mean, right now we don't visualize the data off of Ampool because we actually have in Data Torrent, we actually have a visualization support. So out of this thing, so these snapshot server and uh, the result operators, they actually can directly feed over the WebSocket, directly feed the data to actually the dashboard. So we are currently using that. So you can see these are the various operators and these are the various containers, and they are essentially in active state. There are lots of other cool things on this dashboard. So what I'm going to do now is very quickly I'm going to start my data generation program. So this is AdTech stream generator. So as I said, we actually have simulated. We first populate the bunch of users, a bunch of content pages, and bunch of advertisements, and then we actually generate the ad server log, which is nothing but a given user ID. This content ID was shown, and this particular ad was displayed, and then event was like clicked or viewed. So we randomly generate this ad server log. Also, we randomly generate some updates to the user's interest. So we keep on changing the interest of users. So you can see a bunch of users, contents, ads have been added, and now you can actually see the events have started uh, getting published to the Kafka topic. These events are actually the ad server log events, as well as some of the events are marked as a UCA update. That means user content or ads updates. Those are typically less frequent, where ad server log events are more frequent. So here now you can see actually that basically the whole pipeline started running and so many events have been actually emitted and these things have been processed. The latency is right now high because initially we dumped a lot of data. So as the pipeline catches, the latency should reduce down. Uh, so now we can actually see, for example, top 10 campaigns. So we have basically the data for various e-commerce consumer products, and we just taken those product itself, their information about the product itself as an ad information. And now you can see after certain interval of 20 seconds, the top 10 campaigns are changing. So here it basically shows uh, which are the top three, because in that window only these three campaigns have been shown. Now in this window 4 campaigns have been showed, and typically each campaign there are so many 3 events. Toshiba's 3 events have been occurred. That means 3 ads were shown under Toshiba's campaign and then they were clicked actually. So you can see actually this is running with taking on the real-time ad server log content and showing you how the things change. If you want to see the latency, actually
It is just a simulation, right?
it's a simulations, yes. Still a single node system.
Data generation is essentially acting as a proxy or an ad server log. The rest is all real.
Yeah.
The rest is all real.
Yeah, I mean the actual data is just we have simulated because we don't have actually the real website and ad exchange kind of data. So we are just simulating that, but all that events are actually flowing through this Apex pipeline. They are making the real-time lookup. So for example, in the ad server log, you only have the IDs, ad ID, content ID, and the user ID, but you need to actually during the real-time processing you need to get for that ad ID, tell me the ad platform, tell me the ad basically type, is it mobile ad or is it a web ad, and based on that you may want to aggregate the thing. So all that stuff is really happening with in-memory calls to Ampool. And
Around
10 events, a throughput of around 10 events per second with a latency of 20 milliseconds per event.
Actually, this is single node system, which is running
even for
the
a single
whole.
nodes, it seems.
No. The single node means actually the lot of.
Oh, the generation is only also running on node.
Generation is also running on the same node, so there is a lot of load on the system. Latency is actually, I mean, because of it's a single node, actually it would help.
Yeah.
But still, there is a lot of processing going on, and the number of cores, if you see, are not that high actually.
So what the batch job you're running on Ample? What that's about the aggregations?
Yeah, so actually the batch job is not shown over here. This is only the streaming analytics stuff is shown, but you can actually run the Hive query periodically every hour on the data that basically just we are storing the user content and this thing. Every hour we actually just take a snapshot of this data which is right there in memory, and we run the analytics and find out the best matching ad for a user, and then that we use by making a lookup this thing. Data generator basically takes into that stuff into account.
Instead of running Hive query, are you reading it back to HDFS or something on this data?
No, it's still right. I mean, the Hive query is basically taking the data from Ampool and actually generating the mapping, user to ad mapping, and it's again storing that information back into Ampool. Because that's what we want to actually show the analytics use case for. The Geode, which only supports the key value store. We are now having the analytics abstract. I mean the table store abstraction, which can be used for fast analytics right there.
But if you're running the Hive query, I was thinking you need to write the data on the HDFS so that you can run it. Right?
Hive actually, no, I mean, you don't need to write the data to HDFS.
Okay, it's an in-memory data on that.
Yeah, so what we actually have in Hive, actually, you can actually just change the serializer, deserializers, and the storage, what is it, storage format, storage handlers, so that you can actually just write it into any store that you want. So we have written that for Hive. So Hive logic doesn't have to change. It's just that you configure Hive to write the data into Ampool and read it from Ampool.
Okay. Thank you.
Any more questions?
Any questions?
I have a question. At this point, do you have only one use case, or you are in the process of developing another use case?
So we actually have, this is one use case we have. We are actually doing some of the POCs with our customers and prospects. There we actually have some other use cases as well. So we are working directly.
So do you have a use case on IoT or something?
Sure. So we are working exactly on one of the use cases where they are actually developing the IoT application. So primarily, I mean, we want to show that the same memory store can be very efficiently used for analyzing the data as soon as it lands into memory, as well as you can actually look up and do the transactional operations on that data as well. So combining that both the benefits together. Thank you.
So there's a question on the webinar. Is the dashboard CQ from mtable? Continuous query from mtable?
Yes. No, the dashboard doesn't right now actually use the data from mtable. Dashboard actually currently takes the data in real time from Apex operators, but you can actually as well visualize the data from mtable directly using any visualization tools.
It's after the Geode plus scan operator is done. That's after that.
Yeah. So we can write another operator which can just basically visualize or pull the data from mtable and push it onto the dashboard. So.
Any other questions?
Cool. Thank you.
So I wanted to thank the three speakers for increasing our knowledge and understanding of Geode and Apex with their wonderful talks. I also wanted to thank everyone who's here, people who joined us remotely on the webinar, and everyone who worked behind the scenes to make this meetup possible. And just a quick reminder, on your way out, do fill up the feedback forms that are on the bench behind you, and then hand it over at the entrance and get a t-shirt. Thank you.
Yeah, so should I just close down, right?
I'm going to turn off the webinar. Thanks everyone on the webinar for joining.